Hello, cherished students, and welcome back to the Statistics and Mathematics Tutors course on stochastic processes. So in today's video, we're going to look at branching processes. So stay tuned and let's get into the video. So branching process is just a very simple concept or stochastic process. So I want you to just relax, don't panic, and let's get to the root of it. What is it about? So usually, branching process is one of the mathematical ways of simulating growth or reproduction in units or entities with the passage of time. This is used in various applications, for example, actuarial science, statistics, genetics, biology, for modeling units whose reproduction dies in other ways. So, from the aristocratic family, that the geniuses, Einstein, those geniuses, they came to see that we've been studying about genetics. Charles Darwin brought about the concept of this reproduction and so forth. So how is it applied in probability theory? That was the major question that came up, and this question actually was posed by Galton Watson. Okay, so this Galton Watson was actually a half cousin of that of Charles Darwin. Yes, Charles Darwin's half cousin. So he thought about this as something that maybe we can apply probability theory to see the longevity of species that actually nature produce, right? Yes. So how's the population going to grow? So if you look at a particular species, how is it going to be? Is it that in the long run the species is going to go extinct, or is going to survive over time? Okay, yes. So he did this like somewhere in 1873 with a friend. Okay, so this friend was called Henry William Watson. So Francis Galton, like I said, who is a half cousin of Charles Darwin, in later life developed some less elegant ideas about reproduction. So this is what the branching process is all about. So they named this whole thing the Galton-Watson process, which was brought by Francis Galton and the friend Reverend Henry William Watson in 1873. So when you hear Galton-Watson process, it is the same as the branching process. This model was named after them. So now let's see from Charles Darwin's theory of evolution. As you can see, Charles Darwin said that somewhere in 1871, okay, early 1859 there, I think he brought about the concept of evolution. Okay, so but he did not actually study into like this with respect to him. He just said there's something called evolution. Species actually came from something. Okay, so somewhere in 1871 later, he brought the concept of human beings evolving from some man-apes and not created by God in his own image under the Garden of Eden. This was Charles Darwin's belief. All right, yes. So he said that the environment produces more than nature could take care of, the species that the environment produces. Okay, so this is where most of you hear the concept survival of the fittest. So because of the numerous species that were created, they find it difficult to get food to eat. So usually the strongest one could go far to get a better food to eat, and as a result they improve in diet and they change. So you can see the transition. This ape has the hair, the fur is on it, following to the other one. You realize that there's some kind of improvement. So as they get better food to eat, survival of the fittest, they became better improved. So the man holding the coffee over here, which is somehow, this is Charles Darwin's idea about evolution. Okay, just that his cousin, half cousin, actually want to apply the theory of probability to the concept of what this evolution. Okay, yes. So let's look at the Galton-Watson model. What they said that we should consider some sort of population consisting of reproducing individuals. So by reproducing individual, we mean living things. This could be animals, it could be plants, bacteria, royal families. It could be diseases, it could be computer viruses, it could be rumors, gossip, lies, and so forth. Anything that you think that like can spread, or it has the capability of being like extinct or surviving, something that can spread very large, yeah, something like that. We know that living things can either survive or they can die at any point in time. So we want to study, and this is our probability because it's probable either they will survive or they will die. Yeah. So the model proposed by Watson was the following. He said that a population should start with one individual that is at the initial stage, that's n equal to 0. So the initial individual, this is the initial ancestor. For instance, if it is cocoa that we are looking at, we want to say that Tete Kwashi brought cocoa to Ghana. So what was the, like, maybe it was a one species he brought. So let's look at the evolution of cocoa. Is it going to go extinct in Ghana or even just in like West Africa? Yeah, so but we are saying that it started with just one cocoa plant. So that's what we are trying to say. So the Galton-Watson process says that the origin of the population that we are going to study over time is going to begin with just one species. So after 1 unit of life, at time n equal to 1, the sole individual produces Z1 identical clones of itself and dies. So I'm trying to say that if you pick a human being, for instance, there's no human being that has more than one life. Your life is just one. So once you produce an individual or you give birth, your lifetime will definitely end. So the Z1 is like the family of Z0. Z0, this one individual is going to produce to like identical clones of itself, like you give birth. So this, in this case, we're not looking at maybe a husband and a wife mating or something. When we pick the husband, maybe as a human being, we are looking at the generation of like what the husband's generation is going to be like. We're just studying one species and see how it's going to be. So that's Z1. So Z1 is the family size of what the one individual, which is Z0. Okay, yeah. So remember, Z1 is an integer and not integer valued or random variable. This is what we're trying to say. We know that the species is like they are countable. So the number of species that environment can actually produce, or the human being, let's take human beings for instance, we cannot have 0.5 human beings or 0 human being. It can either be 1, 2, 3, and so forth. So this Z1 and the subsequent Zn, which are the family sizes, are supposed to what, like be integer values with 0 exclusive, right? Let's proceed and look at the modern difference. So how many offspring? So we're saying that that's what I said in the previous slide. So this offspring could be 0. Maybe 0 means that you gave birth to not, like, maybe for in the case of a human being, maybe the person is barren and has not produced any child. If it is 1, it means the family size is going to be 1, 2, 3, and so forth, right? So this is the family size. Why? So I'd rather say that if we have someone that's a human being giving birth to some sort of family, so the family size of that one person is going to be denoted by Y. So Y could be any of these we spoke about, right? So Z1 happens to be, if Z1 happens to be equal to 0, then the population is dead and nothing happens at any future time n greater than or equal to 2. Yeah, as we see. So let's look at the model assumptions. So I'm trying to say that all individuals reproduce independently of each other. So if the initial ancestor gives birth to 4 children, each of these individuals can reproduce, like they can also get their own family sizes independently. The fact that child 1, child 2, child 3, and so forth are giving birth, it doesn't mean that they should all give birth to the same number of individuals, or the dependency, maybe if the first child is giving birth, the second child is also giving birth. No, they should reproduce independently of each other, right? And there should be identical distributions of the family sizes. So the family sizes of different individuals are independent and identically distributed as in their IID random variables. So each of them is denoted by the family size Y. Okay, yeah, that's where the identical case comes. So they are all following some distribution, just that the family sizes may be different. Let's say if the family size follows binomial distribution, is going to follow for all the children or in the generation. That is what we mean by that. And we also have discrete generations. Yeah, as in we divide the generations into discrete, like the first generation, second generation, third, and so forth. And the number of children in each of these generations also are discrete. Like I told you, we cannot have negative human beings or maybe offspring in each of the generations or the family sizes. So that's the progeny assumption. Okay, so let's look at the family size distribution into details. Let's see what that is going to be, but we'll pause here and look at it in the next video. Thank you so much for watching this video, and God bless you.